Okay, so I think I'm recording. Let's start the lecture. Welcome everybody to the next theoretical lecture. Today, Professor Aki couldn't attend to provide the theoretical lecture, so I'm going to substitute him. As we do in the tutorials, I would like you to interact, to ask as many questions as you can. And today's lecture is really important. Okay, we are going to learn about the hydraulics modeling, which is a paramount lecture in your course. And we will do some exercises too, and I will try to connect as much as possible what we will do today with the tutorials, okay? So please, as we usually do, any questions that you have, please feel free. Usually, you know that Aki streams the lecture in YouTube. I'm using the tutorials meeting link, but I will upload this video to YouTube, okay? So that you have everything. Students online, you hear me and see everything well, no? Can you confirm? Perfect. Okay, so let's start. In the previous lecture with Aki, you were learning how to model the hydraulics, and in particular, you studied the properties of the liquids and stopped in the lamp fluid theory. Today, I'm going to start with the next lecture, which is the flow types. Okay, I don't know. Have you ever had or course or had a course related to fluid dynamics? So probably what I'm going to show you today, you already know it, but it is necessary for the upcoming content that I'm going to present. So let's start. As you know, as in many nature phenomena, for example, you can have a flow heat, okay, with different temperatures, and this flow heat will go from the highest temperature to the lowest temperature. In this case, if you have a pressure difference, you will have a fluid flow that tends to equalize these pressures, okay? And this flow type is very important in hydraulics, okay? Do you know the two types of flow that you can find in hydraulics? Laminar and turbulent, right? I think that we have already mentioned this in the tutorial. So today I'm going to show you the two types of flows. You know that in the laminar flow, you have a fluid that moves smoothly, and you don't have a chaotic motion with whirlings or eddies as in the turbulent case, okay? You have a steady, let's say, a smooth flow. Whereas in the turbulent flow, the fluid whirls in a way that the particles have no specific trajectory, okay? You would have a chaotic motion and irregular motion. We are going to learn how to model these two flows. So have you ever heard about the Reynolds number in this fluid dynamics course? For those that don't, the Reynolds number is a dimensionless quantity that consists of a ratio between the viscous forces and the inertial forces, okay? So basically, you have a critical number of this Reynolds number. That is the one denoted in your slides as RE critical with the KR here, okay? And this critical Reynolds number determines the transition from the flow laminar to the turbulent flow, okay? From the laminar flow to the turbulent flow. This, let me check that the streaming is working well. Yeah, I think so. This this Reynolds is a function of the geometry of the pipe, for example, that we are considering. I will show you now different cases. Okay, so basically, what you need to know related to the Reynolds number is that when you have low Reynolds number, the viscous forces are dominant, and you will have what? Laminar or turbulent? Do you know? Low Reynolds number is usually associated with laminar, exactly, because if you have a ratio of inertial over viscous forces and the viscous forces are dominant, you will have laminar flow. Whereas if you have a higher value in the Reynolds number, you will have a turbulent flow, okay? That is shown here, okay? The flow is laminar when the Reynolds number is lower than this critical Reynolds, and the flow will be turbulent if the Reynolds is greater than this critical Reynolds number, okay? Is what you need to know. Perfect. As mentioned, this Reynolds number varies greatly with the different properties, as for example, the geometry, different flow ports. I will show you now. For a pipe, okay, in a pipe, you can write these Reynolds numbers as shown here, okay? And be careful with this notation, okay? You can see that you have here two V's, okay? This first one, if you want to take notes, it would be recorded in the lecture, so no problem, is the mean velocity of the flow, okay? Mean velocity of the flow times this dh, which is the hydraulic diameter, okay? So basically, you would have here mean velocity of the flow and hydraulic diameter over the kinematic viscosity. Do you remember what is the kinematic viscosity from previous lectures? How can you compute the kinematic? I will try not only to provide new material, but also to review everything for the exam, okay? So do you remember how to compute the kinematic viscosity? If you remember in the tutorial, we were introducing this numerical value too. So this kinematic viscosity is just the what is called dynamic viscosity that you usually denote by mu divided by the density of the fluid, okay? It is just this kinematic viscosity. So yeah, as mentioned, in the denominator, mean velocity of the flow times the hydraulic diameter. In the case, for example, of a circular pipe, you would have here the diameter of the circle over the kinematic viscosity, okay? Clear the definition of the Reynolds number and the transition between these flows? For the students online, please interrupt me, react, or ask whatever you need, okay? Clear so far? It's very important that you understand the significance of this number as the ratio between the viscous and inertial forces, and that it determines the transition between laminar and turbulent flows. Perfect. So let's continue. Let's start with the laminar flow, okay? In the laminar flow, I'm going to start first writing the expression of the volume flow rate as a function of the pressure, okay? So in the laminar flow through a throttle valve, for example, this volume flow rate varies linearly with the pressures. So basically, you can see here the expression, okay? Q is equal to a constant, which is the coefficient in the laminar flow rate, times the delta P, where delta P is the pressure difference, okay? So you can see linear expression. And from the point of view of flow losses, from the point of view of energy, you have to know that in the laminar flow, these losses linearly depend on the flow velocity, okay? In the laminar flow. So two important things here. The volume flow rate depends linearly with the pressure difference, with the delta P, and from an energetic point of view, in the laminar flow, the flow losses depends linearly with the flow velocity, okay? Is the other thing you need to know. Perfect. And this CL is just a coefficient of the laminar flow rate. This CL will depend on the geometry of the pipe that you have. I will show you now different cases where you will see all the parameters that this CL encapsulates or considers, okay? Yeah, as mentioned here, for the most typical laminar throttles, there are analytical formulas to compute this CL, okay? I will show you now the different geometries. So, for example, in the case of a canal, okay, with rectangular section, as you can see here, this would be the expression of the CL. Remember, always the same structure. Q equal to CL times delta P. So this would be the CL. For the most typical case of a circular pipe, this would be the CL, okay? CL times delta P. If we consider now a circular crown, as shown here, this would be the expression. You can see that it changes, okay? It changes. But in all the cases, it's a function of the geometry. This D would be the diameter, for example, the diameter of the circle. This eta would be the viscosity. And this L that appears always in the denominator is the length, okay? The length of the pipe. So as main, let's say, dimensions, you would have the length of the pipe. And in the case, for example, of the circular pipe, you would have the diameter here. In the case of the rectangular shape, you would have the cube h here, okay, where h would be the height. And yeah, a similar case here with the circular crown. Of course, you can consider more complex geometries as this one, which is a circular crown, but with different thickness, okay, here. So this would be the expression. Conclusion. Volume flow rate equal to a coefficient that depends on the geometry and other parameters, as for example, the viscosity times delta P. Some questions so far related to the laminar flow? Clear? Perfect. Now let's move to the turbulent, but let's first check students online. Do you have some question? Everything fine? By the way, I'm seeing that there are many more attendants with respect to the tutorials. I imagine that you watch the videos of the tutorials afterwards, right? Because there are 52 students online and more people in person today. Okay, so Thank you. We have positive reactions here, so I think that students understood the laminar. So now let's move to the turbulent flow. And in the turbulent flow, in the same way that I exposed the ideas with the laminar, same two ideas here, but in this case, the volume flow rate, you can see this Q is not a linear function of the delta P, of the pressure difference. In this case, you have a quadratic dependence, okay? And this quadratic is given by this square root. So you can see that this CD is discharge coefficient, so a parameter. This A is the area of the throttle. You have inside the square root this 2 over rho. I think that maybe I can mention something related to this. If not, I will review everything today. But all these are parameters. This is the density of the fluid, the discharge coefficient, and you have the delta P inside the square root. So you don't have a linear dependence, okay? This is the turbulent flow. And this dependency with the square root is the most typical expression that you will find for volume flow rates in this course, okay? So arrive to this point. And the other thing that I wanted to mention, in the same way that in the laminar flow, the flow losses from an energetic point of view depended linearly on the flow velocity, here the losses depend quadratically on the flow velocity, okay? Quadratically. So the losses are proportional to the mean velocity of the fluid squared, okay? Proportional to the square of the mean velocity of the fluid. Is clear so far? Perfect. So if you are following the slides with this, I'm going to move from the slides called week 9 in Moodle to the slides that have been uploaded today that are week 10, okay? With this, we are going to properly start the lecture 10, okay? You have both the slides in topic 9 and topic 10 in Moodle, okay? In case that somebody wants to follow the lecture following the slides. Everything fine so far? I imagine that you will interrupt me if you need anything, okay? Perfect. So today, I'm going to focus on the modeling of the hydraulic components, okay? So far, we have talked about the properties of the liquids. You talked, if I remember correctly, about the bulk modulus the other day, the viscosity, the lumped fluid theory, and now we have presented the flow types, okay? Now we are going to talk about the hydraulic components. And in particular, in the hydraulic components, we are going to study the throttle valve, the directional control valve, a type of valve that is called pressure relief valve, this hydraulic cylinder, and the pump. All these components, or most of them, have been already presented in the tutorial of last week. If you remember, we built this hydraulic circuit. It was a simple one, but we already presented most of these components, okay? So let's start with them. But before that, I have included here some pictures with applications of hydraulically actuated mechatronic machines. So you can have, for example, here, two log cranes of different companies, Valmet and Ponce. And basically, you can see here a crane that is hydraulically actuated. So you can see the hydraulic cylinders here. Let me increase the slides. I don't know if it will work. No, it's not working. Okay, so any case, you can see the hydraulic cylinders here, and basically each of these hydraulic cylinders actuate on the booms of the crane, okay? And well, this is an example of hydraulically actuated systems. I show here the machinery, the forestry machinery from outside, and here from the inside. So you can see with this, what I want to show you is that hydraulics have been used for many years, but you can see that in terms of the actuators, it hasn't changed much. But the most important changes, let's say, appear from the user point of view. So here, for example, in the first machine, you can see different levers, okay, to actuate on the actuators. And here, for example, in the Ponce Elephant King is the name of this machine, you can see a more, let's say, sophisticated, okay, control. In practice, it's the same, because what you are doing here, if you see, is acting on these cylinders, which have not changed much from outside. But from the point of view of the user, you can see these changes here, okay? But in any case, same idea, and the hydraulics have not changed much in the previous years, okay? Is what I wanted to show you. This from the application point of view. Now, as a summary of previous lecture, and this is very important, okay? I'm going to try to review everything for the exam. If you remember from the previous lecture, you were using the lumped fluid theory to model the pressure evolution in different control volumes. You studied this, right? So basically, the idea is that we are going to divide the hydraulic circuits in different control volumes, and in each control volumes, we are going to have this differential equation, okay? That governs the evolution of the pressure in this control volume. So in the left-hand side, you have the time derivative of the pressure. And in the right-hand side, I would like to ask you some things to see if you understood. So this term, this VE, what is it? Somebody can tell me? As in the tutorial, okay? There are no wrong answers. Please feel completely confident to reply. There is no problem if it's incorrect, okay? So do you remember what is this BE? Bulk modulus, and in particular, thank you, Johnny. Okay, bulk modulus, and in particular is the effective bulk modulus. Okay, because you can have in a control volume the contribution of different, let's say, elements. Okay, you can have a container, you can have the oil, you can have a hose. So this effective bulk modulus takes into account all these contributions. Okay, this V, do you know what is it? Is the total volume, okay, of the control volume that we are considering. And now, what I'm going to focus now is in the signs of this parenthesis, okay? This QI, do you know what is it? Sorry? It's not initial, it's incoming, okay? Incoming. And it is because in a control volume, you can have volume flow rates that are entering and others that are coming out, okay? So for those volume flow rates that are coming inside the control volume, you have a plus sign here, okay, QI. For those volume control, so for those volume rates that are coming out, you have a minus sign here, minus QO. And this final term, do you know what does it represent? Exactly, it's the change of volume inside the volume control that in practice, if you think about it, with all the elements that you have studied so far, corresponds to the piston movement, okay? So if you have a piston movement, it will be increasing or decreasing the volume in the chamber, okay? We will see now several examples to practice. So for the students online, is it clear this equation? And remember, this equation is given by the lumped fluid method, okay? Perfect. All clear? Yes, please. Yes. We will study now some examples, but yeah. If you remember in the tutorial, how we were doing this? We were not introducing explicitly each of the parameters, but for example, the hose, the volume of the hose was a field that was called dead volume. Do you remember? So we were considering with that the volume of the hose, okay? But here you will see now in an example that we are considering everything, okay? Sometimes the volume of the hose is very small, I have to say that. But in this particular case, I'm going to show you how to take into account everything, and we will neglect it if it's very small, okay? In this example, for example, lumped fluid theory, okay, is commonly used, as mentioned, to model hydraulic systems. And you can have here, for example, a throttle. Let me check again. I don't know why it's working so slow. Let's be a bit patient. Okay, now it works better. Okay, so you can see here a throttle, okay? And this throttle basically is separating two control volumes, okay? So the symbol of the throttle is this that you can see here. And you can see a first control volume that will have its own differential equation. And this second control volume, we have a different differential equation, okay? It is not specified here, but you will have here a P1 and here a P2, okay? Here you will have an effective bulk modulus, and here you will have a different one. I will show you an example now to practice this, okay? So let's go. Replying to your question that you asked me before about the volume of the hoses, let's do this exercise, okay? So basically, you can see that we have here, when it charges the image, a piston, okay? A piston that has surface or area A, okay? We model the motion of the piston with this X, and the velocity is X dot, okay? And we have an incoming volume flow rate that is QI, okay? And the question is, write the equation to calculate the pressure. So basically, using the lumped fluid method, write the differential equation that governs the time evolution of the pressure in this chamber, okay? Perfect. So any idea? How should I start here? How should I start? Think about the equation, okay? Remember, in the left-hand side, you always have the time derivative of the pressure. That is what we want to compute. And in the right-hand side, we have first a fraction, okay? The effective bulk modulus divided by the volume. So we will have to compute first the effective bulk modulus, and the volume, okay? Is what I'm going to do right now. Always proceed in the same way with these exercises, okay? First, prepare all the ingredients, which are basically the computation of the effective bulk modulus and the volume, and then we will write the differential equation, okay? So let's start. And the first thing that I'm going to compute here is the volume. Replying to your question, total volume that I'm considering in this control volume. The control volume is what has oil, okay? What you can see here with the waves, okay? With the fluid. So first, this rectangle here. Sorry? You can see the mouse? Let me see. Now you can see, now better. Okay, with this laser tree. Okay, so I don't know how you can see that, but with this is better. Okay, so we have here the oil, okay? And this, as you can imagine, this volume depends on the motion of the piston. So do you all agree with me that if the area of the piston is A and the displacement of the piston is X, this volume is surface times this displacement, which is A times X? Perfect. And now the other contribution to the total volume that I have is this volume here, which is the hose, okay? So the total volume V is VH, which is the volume of the hose, plus AX. AX, what is inside the container or the cylinder, and VH. Now, to compute the effective bulk modulus, well, let me check because in this mode, I don't have access to the chat. Students online, do you have any questions so far for the computation of the volume? Yes? I have a comment in the chat here. No, it was the reply to the first question. 1 second, I think I have clicked something. Okay. Okay, so let's continue. Everything is fine so far, no? Remember to consider the volume of all the elements inside the cylinder and this volume of the hose, okay? Clear? Perfect. So let's move now to the other computation that we need to calculate, which is the effective bulk modulus, okay? And do you remember how to compute this effective bulk modulus? Sorry, the difference between what? But basically, as in the volume, if you think about it, we took into account all the different sources. So we took into account the hose and what we have inside the container. Now, basically, remember the bulk modulus, what represents is the flexibility, okay? It gives you an idea of the flexibility. So and of course, each of the components of your hydraulic circuit has a different contribution in the flexibility. So you need to take into account all these sources, okay? In this case, always the equation is this one. 1 over the effective bulk modulus is equal to first component that you have in the hydraulic circuit, oil, the fluid, okay? So all your volume, the structure of these components, I imagine that you reviewed this with Aki, but you always have a volume here in the denominator. Each of these fractions is a contribution, okay? So for example, in the case of the hoses, let's put the contribution of the hoses to the volume modulus. You put the volume here in the denominator, so volume of the hoses, by total volume. Total volume is volume of the hoses plus containers, so VH plus AX, times volume modulus of the hoses. Always, each of these contributions. Now, contribution of the container or the cylinder. Volume of the cylinder, which is A times X, over total volume, which is VH plus AX, times the bulk modulus, okay, of the cylinder. Understood these two contributions? So always nominator. The sub-volume that I'm considering, hose in this case, container in this case, nominator, total volume times the bulk modulus of the element that I'm considering. And in the case of the oil, you agree with me that everything has oil, right? Both the hoses and the container. So you would have in the nominator V, total volume, okay, over or divided by total volume times VO. You would have the total volume in the denominator. You just write 1 by VO. Is clear? So basically, to compute the effective bulk modulus, you do first the contribution of the oil, next the contribution of the chamber of the cylinder, and then the contribution to the flexibility of the hoses. Okay? Is it clear how to compute each of the fractions, the structure of the numerator and the denominator? Yes? Please, I can spend all the time that you want with this. Because you will have an exercise of this in the exam probably. So my objective is that you understand it clearly. Is there some question? Is clear? And from this equation, you just isolate the effective bulk modulus, okay? You operate mathematically and you will obtain this effective bulk modulus. But before obtaining this long expression that can be cumbersome in many situations, the important thing is that you do step by step without making any mistake this. Okay, so 1 divided by the effective bulk modulus is equal to, and each of the contribution, hoses, chamber or container, and oil. Okay, is clear? Perfect. Let me check the chat. The screen gets a bit confused every time I do this. Yeah, let's wait. Okay, students online, is it clear how to compute the effective bulk modulus, considering the contribution of each of the elements in the hydraulic circuit? If somebody could react or share some idea, is good? Yes? Perfect. So remember, we have computed the volume and the bulk modulus. There is a question here. Sorry, what does B? Thank you, Jasmine. BO is the bulk modulus of the fluid. In this case, is oil. That is why we are considering the subscript O, okay? And we are going to assume that in these particular examples of hydraulics, this bulk modulus of the oil is constant, okay? If you remember in the tutorials, we're considering a value of 1,500 megapascals. In practice, it is a function of different variables as pressure, temperature, but we are going to assume that this bulk modulus is constant, okay? So basically, if we ask something related to this in the exam, if you have some exercise, it will be just a numerical value that is provided, okay? As in the tutorial, okay? Or in your simulation project work, okay? But it's, yeah, it usually depends on pressure and temperature, but in this case, we are going to assume that it's constant in the hydraulic applications. Thank you. Okay, so let's continue. Let's continue. So now, once we have the bulk modulus, remember, please, that we are writing this equation, okay? This equation. So we have already computed BE. We have computed B. Now, one question. Do I have QI in my example? I have an incoming flow rate, no? Coming from the hose here, no? So in this differential equation, I will have a QI. And what is QO here in this example? What is QO in this particular example? Do I have an outcoming volume flow rate in this particular case? I have an incoming volume flow rate, but I don't have any volume flow rate that is coming out, no? So this QO, without any fear, you cross it in the equation, is 0, okay? 0. And the final term that you have is the term related to the volume change because of the motion of the piston, okay? So this is the volume change term. The time derivative of the volume in the chamber is the area times x dot, okay? Clear? How do I obtain this? Well, you know that V is just the volume of the hose, which is a constant. The time derivative of a constant is equal to 0. And the time derivative of this volume is the derivative of A times X. A is a constant. And X, the time derivative is just X dot, okay? The velocity. So that is why the time derivative of V is equal to A times X dot. Is it clear? Perfect. So basically now, in the previous differential equation, I'm going to write all the elements that I computed. So I have in the left-hand side, P dot equal to, remember, nominator, effective bulk modulus, the expression that we computed, divided by V, the volume. What is the total volume? Volume of the hose plus A times X, that is why you have it here. And now inside the parentheses, incoming flow, QI, I have it here, minus outcoming flow, 0. I don't have any outcoming volumetric flow here, okay? And minus the volume change, which is A times X dot, okay? So is it clear the differential equation in this exercise? Yes, no? Easy, perfect. Very nice. So with this, I wanted to review a bit the lumped fluid theory with this example. And we have also studied the volume flow rates. Of course, now that we have studied the types of flows, if you have now, for example, a turbulent flow rate, this Qi will be a function of the square root of the pressure, okay, based on what we have studied. So you can introduce now in these Qs the different types of flow that we have studied, okay? Perfect. So now I'm going to start with the modeling of the hydraulic components, okay? And the first component that we are going to study is the throttle valve. In this fluid dynamics course that you have studied, did you study any of these components? Yes? Okay, perfect. So for some of you will be something familiar, but let's review everything because probably there are some students that have not studied this. So let's start with the throttle valve, okay? Throttle valve. Basically, in the throttle valve, we are going to assume that it is a short element, okay? And here the flow is assumed to be turbulent, okay? Turbulent. So you know that the dependency of the volumetric flow rate with this pressure will be quadratic, this square root, okay? And basically, this is the geometry that we are going to consider in the throttle, okay? We have here a Q, volumetric flow rate, and remember, every time you have a throttle in or a directional control valve, these kind of elements in your hydraulic circuit, you have to distinguish between different control volumes. So in this case, I have the fluid coming here with Q and a pressure P1. So if I write using the Lamb fluid theory, the differential equation, I will have, as previously shown, P1 dot equal to all the other terms. But now this fluid finds this throttle, okay? In the moment that the fluid finds this throttle, I have to distinguish. Cursor is not visible. Sorry. Thank you very much. I need to use both hands for this. Okay. So basically, we have the incoming flow here. We find the throttle. Okay. And in the moment I find the throttle here, I have to distinguish with a different control volume. Okay. So this would be control volume 1. This would be control volume 2. And of course, in this control volume, you have a P2. Okay. Different pressure with respect to this one. So what you need to know is the volumetric flow rate, QT, Q throttle, is equal to, very easy, okay? This CD is a discharge coefficient, okay? It's called the discharge coefficient, times the section. This section would be the area. So if the throttle valve has a diameter of D, this would be pi times D squared over 4, okay? So this would be the area. And inside the square root, you have 2 divided by the density of the fluid and the pressure difference. Before we were writing it as delta P. Now the gradient of pressure is P1 minus P2, okay? Delta P. But you can see that this modeling is the turbulent flow type, okay? You have the square root of a pressure difference, okay? So turbulent flow rate. Perfect. And to model this volumetric flow, a method called the semi-empiric method is used, okay, to write the equation. So basically, this semi-empiric method, what does is say, okay, your volumetric flow rate is equal to a coefficient times the square root of delta P. And this coefficient basically absorbs all the elements shown in this equation. So this CV is the CD times the area, that is called here A, okay? So this A is pi square of the diameter over 4, and this constant that is inside the square root, which is 2 by the density, okay? So you would have here in the CV these 3 elements, okay? Clear? And you write the volumetric flow rate this way. Let me check if there is some question for in the students online. Some question related to the modeling of the volumetric flow rate. Okay, cursor is not visible. Perfect. So now, is it clear how to model the volumetric flow rate in the throttle valve? Yes? If you have some question, please feel free to ask, okay? Clear? I imagine that yes. Please feel free to participate, okay? So, clear, thank you very much. Thank you. So, what we are going to do now is continuing with the modeling of the throttle valve. Perfect. Now, of course, if you see this coefficient CV, it is a function of several parameters, right? This discharge coefficient, the area, the density. In practice, what manufacturers do is provide what is called the characteristic curve of the valve, okay? So basically what you have is a plot that relates the pressure difference in bars with the flow rate, okay? With the flow rate. So basically, if you see what you have here is the QT, the flow rate, and the pressure difference, the delta P. And this curve here is exactly this constant, okay? The coefficient of the throttle valve, okay? So in many cases, the way to compute this numerical value is going to this characteristic curve, seeing, for example, you want to compute the semi-empirical constant and you are told, I think we're going to do an exercise here. Basically, you can check what is the flow rate, okay, and the corresponding pressure difference, and you can compute the value of CV. Did you understand this? So basically, yeah, you are plotting this delta P related with this QT, and for a given value of flow rate, you can see the corresponding delta P and see the CV. We are going to do an exercise now, okay, to clarify this. And very important, okay, if you do this, look, many manufacturers may provide the flow rate in liters per minute, okay? We are always working, remember, with the international system in this course, okay? So if you had to compute this in the exam, please, the volumetric flow rate, write it in cube meters per second, okay? Cube meters per second. And this delta P, of course, this here is provided by bar. 1 bar is equal to how many pascals? Sorry? 14? No, no, no. 1 bar is 10 over 5 pascals, okay? 0.1 megapascals, okay? Perfect. Probably the 14 is some other unit that you were thinking about, some relation, but 1 bar is 10 over 5 pascals, okay? Perfect. So in this particular case, you have this unit. Perfect. So now the last thing that I wanted to tell you, okay? You have the incoming flow here with Q, pressure P1, and you have this other chamber with P2. There are some times that you might have recirculation of flow, okay? So basically some fluid that came from P1 to P2, you can also maybe have a recirculation and some fluid going from this chamber to the other one. You need to specify in this equation, the sense, okay? The sense of the fluid. So to do that, you have here the CV, which is the coefficient, the square root of the pressure difference. Of course, if you have a square root, you need to write this as an absolute value to avoid an imaginary number, okay? That is why you have here the absolute value. And to determine the sign in your equation, sorry, the sense of the flow, you use this sign function. This sign function is just a 1 or minus 1, okay? And basically it is telling you if the fluid is going from P1, from the volume control 1 to 2, or from the control volume 2 to 1, okay? It's just basically to indicate the sense of the fluid, okay? Because you could have a case where you have the opposite sense, okay? So in general, the expression of your volumetric flow rate will be this constant times the sign function. This is just a 1 or minus 1, okay? And the square root of the pressure difference, okay? Clear? Yes? Perfect. So that was everything related to the throttle valve. Now we are going to move to the proportional control valve. If you remember, sorry, to the directional control valve. If you remember, in the tutorial 6, we already modeled a directional control valve, okay, that determined the configuration mode of our hydraulic circuit. We didn't model a throttle valve, okay? We didn't have a throttle valve, if you remember. We had a directional control valve. But you will see that in practice is very similar. So this is a brief introduction of the valves in general before moving to the directional control valve. This in particular is a pressure relief valve, okay? I will tell you later how does it work. But as you know, in a hydraulic circuit, valves are used to control both the pressure, the flow rate, and the direction of this flow. And these valves are usually controlled by a spool, okay? By a spool. If you remember in the tutorial the other day, we had to define the positive direction of a spool if it was going to the right or to the left, connecting the different ports, okay? So these valves are usually controlled by a spool. And yeah, for the modeling of the valve, we are going to consider two steps or two aspects, okay? First, the modeling of this spool position, okay? And secondly, the modeling of the volume flow. I will show you now all these steps, okay? So this is an example of a directional valve, okay? You have, for example, in this configuration valve centered, you have port P. This is exactly the same example as we studied in the tutorial, okay? You have in port P here the pump. So imagine that we have a pump here providing fluid that leads to a increase in the pressure. And this T is the tank, okay? The reservoir that we were considering the other day. And these A and B are ports, for example, that have connected hoses to a hydraulic cylinder, for example. So you see that in this valve center, there is no communication from the pump, which is the red fluid. Sorry, I think that you are not seeing the now. We have P, the pump, the tank, and these AB ports of the cylinder. So if we consider now the fluid coming from the pump, the red one, in the valve center configuration, the red fluid doesn't reach the port A, right? It is closed, right? And you can see that in the same way, the blue circuit, okay, there is no connection between the blue volume, okay, that relates the port B with the tank. But now imagine that you move this valve to the left, okay? You move the valve to the left, and it's this configuration. You can see that if we move this big rectangle here, this section to the left, now we are communicating the pump, the red, with the port A, right? So we are providing fluid to the chamber A. And in the same way, you can see that the fluid that is coming from B communicates with the tank, okay? Because we have moved also this wider part, okay, in the spool, in the valve, and now you are connecting port B with the tank. Is it clear? Do you see the connection? Perfect. So, question. In this representation that we were doing the other day, to review, this is very important, okay? The first one, valve centered, with these three, with which of these rectangles would correspond? Can somebody tell me? This one, this situation here. Exactly. This situation corresponds exactly to the middle, because these lines that you see here are the different ports. Okay, so you would have PT here, PT, you would have AB, and in this configuration, you are communicating nothing with nothing. So you don't have connection between P and A, you don't have connection between B and T, so nothing with nothing is the center configuration, okay? Now, if we shift the valve to the left, we are communicating the pump with volume A and volume B with the tank. With which of these configuration in the representation would correspond? Somebody? With the left one, exactly. You can see that this line would represent the pump with the A, and this other line would be the volume B with the tank. Is this clear? Understood, everybody? For the students online, I don't see right now the hands, but if somebody can ask something, please interrupt me, okay? And finally, another possibility is that I move this valve to the right, okay? This spool to the right. And in this particular case, now we are here in valve shifted right, you can see that we are connecting the pump port with the B port, okay? You see it. And now you see that the A port is connected with the tank port, okay? So this would correspond to the final configuration, the cross one, okay? The cross one. So basically now, in terms of physical representation of a hydraulic cylinder, we would be providing fluid from the pump to the other chamber of the hydraulic cylinder, and we would be, the rest of the fluid would be coming from A to the tank, okay? Clear? Perfect. So please, this scheme, have it clear in your mind, because you will find it several times in the course. And please do not forget the physical interpretation, okay? Depending on how you move the spool, you can have these three configurations, okay? Valve shifted left, right, or center, okay? Final clarification to connect it with the tutorials. In the tutorials, we consider as positive displacement to the right, okay? In this particular case, in this image, the positive displacement is considered shifted left, okay? So this port. In the tutorials, we were considering that this configuration was achieved moving the spool to the right, but here is achieved to the left, okay? Clear? It's the only difference. It's just a sign convention, okay? But please Do always understand the representation with the physical motion, okay? It's the important thing. Clear? Yes? Perfect. Let me check the chat. Is it clear the basic introduction for the directional control valve? How does it work for the students online? If somebody could react and confirm this. Perfect. We have some reactions. Thank you very much. Okay, so let's continue. Let's continue. And we have still some things to tell about the directional control valve. So the next thing, this is an exercise that I wanted to ask you, okay? This valve here, which would be the representation of the valve? Somebody could tell me? Before, in the previous figure, you had port P and T in this down part and ports A and B in the upper part. But here you have all the ports depicted in this low part, okay? A, which would be the volume control A, pump port, volume control B port, and tank. So which of these symbols would correspond? Somebody can guess? I can help you, okay? The first one, does it make sense? It doesn't make sense because you, in particular in this configuration, you can see that all the ports are closed or do not have connection between them, right? You can have fluid coming from the pump here, but this control volume is not communicating with the A or the B, okay? So this configuration would be the centered one, and here you always have communication in these two rectangles. So we are going to discard it. This one, for example, could it be? So imagine that I move this spool to the left. I move it to the left, okay? You agree with me that fluid coming from the pump could go to the A? If I'm moving this to the left? Let's rethink it. We are moving this to the left, okay? To the left. So I'm creating a space here if I'm moving. So the fluid that comes from the pump could go inside here if I'm moving the spool here, right? To the left. So I can have a connection between P and A. And if I move this one to the left in the same way, I can have a connection between B and T, no? So this situation with the spool moving to the left could be this one, the one that we saw before, okay? And in the same way, if I move now this spool to the right, okay? You agree with me that the flow that I had, for example, in A, can communicate by means of this canal with the tank? Yes, no? I'm moving this to the right, so the fluid could go this way, following my cursor, okay? And in the same way, if I'm moving it to the right here, the flow in the pump could go to the B, okay? So this would be this cross configuration, okay? Is it clear? Yes, please. Sorry? Yes? Solid part. So imagine this spool, imagine this as a cylinder, okay, with a small diameter here, and it has a wider part here with a bigger diameter, okay? So this is solid. This is where has my cursor is solid. And the fluid, this would be fluid, solid, fluid. So basically you have the fluid coming from the ports, and imagine this with a cylinder with different sections, okay? So this would be the solid. Do you need me to review it now based on this idea to understand it better? So basically imagine that I move this spool to the left, okay? If I move it to the left, you have communication between the pump and the A, okay? And if I move it to the left, you have communication between the B and the T, okay? If I move it to the right, you have communication between A with the tank here, and if I move it to the right, you have communication between the pump and the B, okay? So basically, the representation of this valve would be this one, okay? Why not the third one? This is very important. Because, guys, if you see this, in this representation, in the valve center, you would have a connection between these two ports, okay? You would have this U will represent a connection between two ports. And in the valves, when the spool is centered, you don't have any communication, okay? That is the reason why this B. There is a question. Let me see it in the chat. One question. I can repeat this as many times as you want. Okay, this is important, and we are going to spend time with this. Let me see the chat. There is a question. How do we have the communication from A to the tank, given there is a solid in the way? Okay, let me repeat it. So from A with the tank was the question. Perfect. I'm going to show it to you with the cursor. Okay. So from A to the tank, Amar, that situation would correspond with the spool moving to the right. Okay. And if you move it to the right, you would have the a small diameter invading the chamber A, so fluid can go through here, okay? And the flow that goes through here goes through this canal, and can reach the tank, okay? So imagine again this moving to the right. You are not blocking with this big diameter, this flow entry, so you would have this, okay? The flow could go to here, okay? Is it clear? Let me see the reply. Did you understand this, the exercise and the different connections? Okay. Amar, did you understand it? The connection between the port A and the tank? Yeah, exactly. Exactly. You can imagine it as a cylinder, with different diameters. So basically, you would have here the small diameter, and these two have a bigger diameter and are blocking the flow. And if you move it or shift it from the left or to the right, you unblock each of the ports. Okay, but yeah, it's a cylinder of different sections. This is the big. These two are the big sections, and this is the small. Understood. Perfect. Nice. So let's continue now. Another exercise, another example, okay? About representation. In this particular case, this one, could you also, yes, I will explain it right now. Yes. So I'm excluding option C because option C in the center configuration considers a connection between these two ports. Okay, you can see here the U. In this one in the middle, all the ports are disconnected in the center configuration, but in this one, you have a connection. And now, and you could say, okay, let's see what happens when we have the spool in the center, which is exactly this picture. You can see that with these big diameters here blocking the ports, there is no communication between any of the volumes. So A is blocked, B is blocked, the flow coming from the pump here is constrained here, and the tank is blocked here, okay? So since all the ports are disconnected, that is why I'm choosing B instead of C. Is it clear? That is why I'm excluding it. Yes? I don't remember who asked it. Vishal. Okay, thank you. Perfect. So let's move now to this example, okay? In this example, we have three configurations, okay? And three symbols. So basically, I'm going to start as reference with the previous one, which is this one, okay? So this was the picture that we discussed before. We have the spool in the center. In the center, no connection. When I move it to the left, which is the X positive displacement, you can see the positive displacement defined here, okay? X. You would have this configuration. To the right, you would have this other configuration. And now there are other two configurations. This first one here, you can see that it's exactly the same valve. So the same ports A, P, B, T as this one. But now the difference here is that this spool, the big diameters that you had here, now are a bit smaller. You see them? That are a bit smaller and do not have the same height as the main diameter here. So in the center configuration, you would have a connection between all of them, okay? All of them would be connected, okay? This is the one that we studied before. And this one, you can see that the difference here is not in the height, not in the diameter, the value of the diameter, but in the thickness, okay? So basically, we will see the consequence of this in terms of flow, but the representation of the valve is the same, okay? So all is connected in the center because this diameter is the same as this mean one, and all of them disconnected, okay? No communication between the ports. and this would be the direct, let's say, mode between pump to mode to volume A, and from B to tank, and this would be the reverse one. Okay, clear? Yes, perfect. So now I'm going to present you some notions related to the volume flow rate. Okay, so usually we will see now the equation, but the relation between the volume flow rate, okay, volume flow rate percentage or volume flow rate, we can discuss this in terms of percentage on absolute value, and the spool position is linear. Okay, in most of the valves that we are going to work in this course, in the directional control valve, the relation between the Q and the U, do you remember that in the tutorial we were defining a signal? Do you remember this signal? This signal was a voltage, okay? But we can think this voltage in the same way as a displacement, okay? Because the voltage basically controls the spool displacement, okay? So this Q, the volume flow rate, is proportional to this displacement of voltage, okay? In the directional control valve, it's linear. But well, this would be this classical configuration. So basically this figure, what is showing is that the classical configuration that we work with has a linear relation between the flow and the valve opening, okay? Here it is called X. We were calling in the tutorial U, okay, as voltage, but it's equivalent, okay? It is the same, we're talking about voltage and displacement. But there are other valves, as this one, okay, which is basically the same symbol, but with these two horizontal lines, okay, that is a bit different. And this valve can be found, for example, do you remember the forestry crane that I showed you before? Sometimes in this forestry crane, you need to carry out very accurate motions, okay? So if you think about this, if the relation is linear, a small displacement in the valve can lead to a great variation in the flow, okay? But if you have a valve like this one, where the flow rate is like shown here, you can see that a variation in the valve can lead to a small volume. So this allows you to perform more accurate motions with the forestry crane, okay? So this is called a proportional directional control valve, okay? Okay, that's the case. And this final case, which is the one that we showed before with the thicker cylinders here in the spool, would have this curve. So basically, in the beginning, you would have horizontal, and then linear, okay? Why do we have this first horizontal stage? Because if you move a bit the piston, you still are blocking. Do you see it? That I can move a bit the spool here and still I wouldn't have flow. I need to move it more. I need to move it more to have volumetric flow rate. Did you understand the curve in this case? The difference? Yes. So basically this one is this one, but shifted a bit because of the thickness of these cylinders. Is clear? Yes? Perfect. So, okay, good. I'm going to, you usually do a break with Aki, right? I think, a small break. So I'm going to do a break of 5 minutes and we will continue now, okay? With the modeling of the valve. So far, everything fine? Yeah. Yes? Perfect. So I retake the class at 5:20, okay? 17:20. And I'm going to use this break to ask for the students online if everything is okay. Do you have some questions so far? Yes.
By the way, do we have the quizzes?
We will have quizzes later. Yeah, yeah. They appear now. They appear now. Okay?
Yeah.
Perfect. So for the students online, is everything okay so far? Some question? Okay, some reaction from Johnny. Thank you. Okay. So we retake the lecture in 5 minutes. Okay, so let's continue. Let's go. For the students online, we are going to retake the lecture, okay? Okay, so we have been in the discussion of the directional control valve, we have mentioned several times the motion of a spool, okay? Now we are going to center in this spool, okay? Basically, the reason of the motion of this spool is the force caused by a magnet, okay? And this force of the magnet is assumed to be larger than the pressure, the friction, and other flow forces. And basically, this magnet is, we are going to consider it in the model as ideal, okay? And in this way, we will have a reference or a input signal, and the real motion of this spool will be this reference or signal with a delay, okay? So as in the tutorial, we are going to denote this signal as U, and the reference signal would be U input or U ref, as in the tutorial, and the feedback signal or the real motion will be U, okay? If you remember, so basically this will be the reference and this is the real motion, okay? If you remember, I was mentioning that sometimes we are considering this U as a voltage, and in other situations, we are talking about position or displacement, okay? It is equivalent, okay? Equivalent. The differential equation that governs the motion of this spool, okay, is this one, okay? So basically you have here the time derivative of U, okay? And this is equal to UIN, which is the input or the reference, minus the real displacement divided by tau. This tau is just a delay, okay? So this equation, if you are asked about it, is representing the valve dynamics, okay? The valve dynamics, and between U and the U input, there is a delay that is controlled by this time constant of the valve, okay? This time constant is provided by the manufacturer of the valve and takes into account the delay in the valve, okay? The valve dynamics. Perfect. So basically, yeah, this here you can find some details of the equation, as I mentioned, and how to compute this time constant. Well, usually the manufacturers provide a representation that is called Bode diagram. Have you ever heard about the Bode diagram? Yes? Basically, a Bode diagram, for those of you who didn't hear about it, you will have a course in the second half of the year, which is controlling mechatronic machines, for those of you who attended, where you will learn how to build these plots, okay? But basically, it represents the response in the frequency domain of the system, okay? So you are plotting the magnitude and the phase, and the manufacturers provide this data, let's say, this input, so that you can compute this time delay, okay? This constant of the valve, tau, okay? Basically, in this Bode diagram, for those of you who have studied it, what you choose is the frequency of minus 40 degrees, and you compute the tau using this frequency, okay? The frequency associated with the minus 40 degrees in the phase plot of the Bode diagram, okay? This is to compute the tau. And now, once that we have talked about all the ingredients, I'm going to present you the equation, okay? So basically, well, an important thing, you can see that this is the directional control valve, but in practice, when we jump from one control volume to the other, what we will have is a throttle valve, okay? So basically, imagine this directional control valve as a set of different throttle valves, okay? Directional control valve as a set of adjustable throttle valves that can be modeled separately, okay? And this is the volume flow rate that you are going to consider in the directional control valve, okay? If you remember, in the throttle valve was a constant times the square root of the pressure difference. So in this case, it's the same expression, okay? Very similar. But the only difference is that this coefficient considers the U, the spool displacement. In the throttle valve, you didn't have the spool displacement. Here you have it. So you have basically a constant for the flow rate using the semi-empirical method. That is why it is called semi-empirical constant for flow rate, times the U, which is the spool displacement or voltage, depending what you're considering in your units, and this square root. I'm asking you one thing. This expression here corresponds to a laminar or turbulent flow? Laminar or turbulent flow? Here. This equation is turbulent, exactly. You have the square root, okay, of the delta P, the pressure difference. So what it is told here is that in hydraulics, in many situations with the directional control valves, when you have a small pressure differences, where the limit is given around 1 bar, okay, for pressure differences lower than 1 bar, you can consider a laminar flow. And for pressure differences greater than 1 bar, you can consider a turbulent, okay? But in practice, the laminar flow can be ignored, okay? Because in most of the situations, you will find a turbulent flow, okay? That is why we are writing here this equation, okay? But remember, if you have a small pressure difference, you can consider the laminar regime. In practice, well, one important thing, this is from a numerical point of view. If you have small pressure difference, I mentioned that you can model it as laminar. Do you know another reason why this is done? Imagine that you have a small pressure difference. You agree with me that the derivative of this Q, does it behave well or bad for a small pressure difference? Could somebody tell me? Any of you know how to compute this derivative? So imagine that you want to compute the derivative of Q with respect to the pressure. What would you have? Somebody brave to reply? There is no problem if it's incorrect. If you remember, the derivative of this function, if we are taking derivative with respect to delta P, would have a delta P in the denominator, right? You would have a delta P in the denominator. And think about this. If you have a small pressure difference in the denominator, that would mean that your derivative would go to infinite, right? You would be dividing by something that is very small, close to zero. So that is why when the pressure difference is small, from a numerical point of view, can be a good decision to model it as laminar, okay? Because the turbulent flow is derivative can lead you to a singularity, okay, in the derivative. But in practice, in most of the situations, we use this turbulent flow, okay? I just explained you this derivative issue from a numerical perspective for doing simulations. We will do an exercise where I will show you this, but in practice, in most of the situations, you model the volumetric flow rate with the turbulent expression. Is it clear? Yes? Perfect. So remember, 3 elements in this equation, okay? The semi-empirical constant for the flow rate, this U can be the voltage or the displacement, and the square root of the pressure difference, okay? Perfect. So now you have the first quiz, okay? So you can complete it. I think that I have already launched it. It's the first time that I do it, but I think it should be ready. So if I go to Socrates here, can you find it? Do you already have it? Okay, so oops, sorry. So I have already prepared it and I have it this ready. Yeah, indeed, I have all of the days ready. So you can already solve it, okay? The quiz basically asks you for the physical interpretation of this equation, okay? Of this equation. So students online, you have the quiz 1 ready and you can complete it, okay? I will give you, you can do it during the lecture, right? You can do it during the lecture, so perfect. I can give you 1 or 2 minutes and we can continue. Yes, you have it here. So basically, you are asked about the physical interpretation of this equation. Okay? It is exactly what we have just mentioned. Okay? I think it's very simple. No? So the first option is the pressure drop due to the valve, the flow through valve, the next spool position, and finally the number of ports in valve. Okay? Let's give 1 minute and we continue. Yes, you have it? Yes? All of you in this sector? Yes, perfect. So what is the correct answers? Can somebody tell me? Huh? Sorry? This equation? Yeah, take into account that where is the pressure drop here? You don't have a variable, the variable pressure drop, okay? You have the spool displacement, okay? Or the voltage. So it's the differential equation governing the spool position, okay? Remember that the equation for the pressure drop, you would have a differential equation for the pressure in the control volume, okay? But not here, okay? Did you understand the reason? Yes? Okay, perfect. Okay. So, students online, did you complete the first quiz? Sorry, let me see. Yes? Perfect. Okay. So let's continue. One second, I'm going to connect the battery. Okay. How do you usually do it? Do you show the correct result in Socrative 2 or yes, no? Okay. So I have to click in show results. Okay, so there are most of you replied the spool position. You understood, did you understand why it was a spool position, right? Number of ports. I mean, if you see the equation, the only variables that you have is the reference in the voltage or displacement, the displacement itself, and this is the time derivative. You don't have, and this tau is the time constant, okay? You don't have any flow, pressure drop of number of ports, okay? You just have the spool position, okay? Perfect. Perfect. So let's continue now. And this is a very important exercise, okay? In the exam, you will probably have something similar to this. So please pay attention to this because I'm going to stop in detail so that everything is clear. So now we are going to consider the previous directional control valve, okay? And I'm going to consider the three configurations. So basically the valve in center position, shifted right and shifted left, okay? Left and right. So and I want to compute these volumetric flow rates. So basically QA, QP, QB, and QT. So let's start with the valve in center position, U equal to 0. Can somebody tell me what is the value of the volumetric flow rates in center position? Huh? 0, exactly. Remember, in center position, you don't have any of the ports connected. So all the volumetric flow rates are equal to 0, okay? You have them here, okay? Perfect. Now, for U greater than 0, which is equivalent to moving the spool, yeah, in the tutorial was right. But remember, here we define the positive displacement X here to the left. So remember that in this exercise, is to the left, okay? It's not bad that this happens because there is not a, let's say, accepted sign convention, okay? So in the exercise of the tutorial, we agreed that it was to the right, but here is to the left. So now, first question that I ask you, to the right, I'm sorry, to the left, positive displacement. Port P is connected with which port? A, exactly, A. And in A, we have a pressure PA and a QA. So could somebody tell me what is the expression of the volumetric flow rate between P and A? It is exactly the expression that I mentioned before, right? So basically, this QA is a directional control valve would be the constant using the semi-empirical method, CB, the displacement U. Remember, always in the equations for the turbulent flow, okay, you have to consider this sign function. It's just a 1 or a -1, taking into account the sense, okay, of the flow. So this would just be a 1 or -1, and now the square root, okay, with the absolute value. Since I'm connecting port P with port A, because I'm moving this to the left, is the absolute value of PP minus PA. Clear? Perfect. Now, in the same configuration, we are moving this to the left. So port B is connected with, with port T, with the tank. Is this clear? So we are connecting B with T. So the equation is equivalent. Basically, you would have the constant times U, but now we have to take into account the sign of PT minus PV, and in the square root, the absolute value, what we put is the pressures of the control volumes that are connected. So basically, the tank with the V. Okay? Clear? Yes? Perfect. And of course, by continuity, if QP is going into QA, QP is equal to minus QA, and QT is equal to minus QB. Okay? Yes? Perfect. The configuration U equal to 0, we already wrote it, and now I would like you to help me to write the equations for the configuration of the spool moving to the right, okay? Moving to the right. So if I'm moving the spool to the right, I'm relating port A with what? With T, exactly. Perfect. You would have the flow moving through this canal to the tank, okay? You see it there, no? Perfect. So the equation in the same way would be QA equal to constant CB times the U, the sign, always consider the sign, and now you would have the square root with the absolute value of PA minus PT. Okay? Yes? Perfect. And now, if I'm moving this to the right, I'm connecting port P with B. Perfect. So QB would be the coefficient, volumetric flow coefficient using the semi-empirical method, CB times U, sine of this difference, and always the square root of the absolute value, okay? Please don't forget this absolute value, okay? Because in many situations, if you do, for example, your simulation project work, you might have recirculations of flow between different ports, and this could lead to a minus sign inside the square root, okay? And have an imaginary number. And of course, a volumetric flow rate is a real number, okay? It's not, it cannot be a volumetric unit number, okay? Is it clear? Perfect. Some question related to this exercise? This is very important. In the exam, you will have something similar to this probably, okay? So you need to learn how to write the equations for the volumetric flow rates depending on the configuration of the directional control valve, okay? Clear? For the students online, did you understand it? Yes? Let me see if there is some reaction, okay? There are some. Everything is good, no? So far? Okay. Thank you. So let's move now. The next thing that we are going to study is what is called, I have finished with the directional control valve, okay? So far, we have learned two components, throttle valve and directional control valve. And now I'm going to move to the concept of digital hydraulics, okay? As I mentioned, hydraulics have not changed much in the previous years, okay? And the hydraulic cylinders that you can see are basically very similar to the ones that were before. But let's say the progress or the advances related to the hydraulics are more from the control point of view, okay, in this modeling of the valves. So related to this, there is a concept called digital hydraulics that basically tend to substitute these valves that use a spool, because imagine if you have a spool moving, that could lead to what? You can imagine leakage of oil, okay? So the tendency is to use this. There is a, there is, somebody shared something. I will check it now, okay? Thank you. So there is a tendency to have this digital hydraulics and considering different valves that are binary valves or on-off, and allow this spool displacement to avoid leakages, okay? As happened with this directional control valve. So basically you have here, for example, the difference. You would have a hydraulic cylinder here that is controlled with a directional control valve with a spool. And with the digital hydraulics, basically you are controlling the cylinder with four flow control units that are called, okay? I will show you now. I have prepared here a video that I want to show you. So let me check because we have some questions before the video. Let me check them. In case, sorry, I didn't see the question, Tommy. I apologize for that. So, sorry, this is to last slide sign. Yes, exactly. The sign function is either 1 or -1, and you open the add in Wikipedia the sign function. Yeah, okay. Let me clarify it in case somebody has some doubt. Yeah, but basically the sign function, you can see that it is either -1 or 1. Okay, this is just like that, what I was mentioning. Okay, this is just the idea, exactly. Thank you for the clarification. I didn't see the question. If this happens again, please interrupt me in the by voice, okay? Sorry for not replying, Tommy. Is it clear, the sign function? Yes? I imagine that yes. Okay. Perfect. Perfect. So let me show you this video related to the digital hydraulics, and you will understand much better the concept, okay? It should work. Yes.
Digital hydraulics, the system variables, pressure and flow, are controlled with multiple on-off directional seat valves. Each valve is solenoid operated and has only two possible positions, on and off. This is why the term digital is used. These valves are used to implement all valve functions, such as pressure, flow, and directional control. Contrary to a traditional hydraulic system, which has many different types of valves, a digital hydraulic system has a large number of only on-off valves. By connecting in parallel three on-off valves of different sizes, such as 1, 2, and 4, 7 different flow quantities can be achieved. 5 on-off valves can achieve the control resolution of a traditional proportional valve. A group of on-off valves in parallel make up a digital flow control unit, called DFCU. At least 4 of these units are needed to substitute a proportional valve in a hydraulic circuit. Each DFCU is used to control one of the 4 control edges. The main benefit of digital hydraulics is the ability to control each control edge independently. This reduces power loss and enables precise control. Additionally, seat valves have zero leakage, as opposed to the high leakage of proportional valves. However, the challenge with digital hydraulics is the complexity of the control algorithm. Each valve needs to be controlled individually, and this results in large numbers of valve position combinations, although each valve has only 2 possible positions.
Okay. So as a summary, in digital hydraulics, what you have is a set of on-off valve, okay, binary positions that can be combined, and as main advantages, the reduction in the leakage, less power loss, and an accurate control, and as a drawback, okay, or inconvenient, more. I'm sorry, and you don't need to employ complicated algorithms, okay? So now let's move to the next quiz. So please, you can access to the quiz. It is already prepared. So please, the question, in case that somebody doesn't have access, is digital direction valve consists of, and option A is a spool controlled by a computer. Option B, a number of on-off valves. Option C, sorry. Is it not activated? Okay, let me do it. Now it is? Yes, okay. Sorry. Okay. So basically, perfect. Okay. So I give you a couple of minutes. Digital direction valve consists of, as mentioned, option A, a spool controlled by a computer. B, a number of on-off valves. C, a spool controlled by a magnet. And D, a spool that moves incrementally, okay? Consider what we have learned in this and the difference with a traditional directional control valve, okay? Okay? Did you all reply to it? Yes? Perfect. For the students online? Yes? Solved? Perfect. So what is the correct answer? B, exactly. A number of on and off valves that can be combined. Perfect, thank you. So let's see the results. Okay, still there were some students that said a spool controlled by a computer. Well, all the other options can be found in a traditional directional control valve. Okay, this is spool operated by a magnet, a spool that can move incrementally or using some computer algorithm, but the digital hydraulics properly set, it consists of this number of on and off valves. Okay, clear? Perfect. So let's continue. And now, this is really important. Okay, so I have received many questions related to the simulation project work on the tutorials, but nobody asked me something that can be found in the exercise, and it's related to that. Okay, what I'm going to say. So basically, in the same way that in the throttle valve we had this curve of the manufacturer to compute the coefficient CV, in the directional control valve it works in a similar way. So basically, this is an exercise. Okay, it says a manufacturer gives properties for a proportional valve according to this picture. So basically, the manufacturer is providing a flow, okay, as a function of U, is in this case in voltage. Okay, and it says the nominal flow with full opening, is 24 liters per minute with a 35 bar pressure difference. Define the parameter CV. Have you started the simulation project work, the hydraulic part? Probably many of you have already done the mechanical part, no? But not the hydraulic. So if you read the hydraulic part, you will read something related to this, okay? You will have a data related to the nominal flow with a pressure difference, okay? So you can find here how to compute this coefficient for the directional control valve, okay? So if you remember, the expression for the volumetric flow rate was Q equal to the coefficient times U and this square root of the pressure difference, okay? Now, in the curve of the manufacturer, we have the volume flow rate and a given pressure difference, okay? So the way to compute this CV is we go to the curve, okay? And we say, okay, I'm going to isolate from the expression the coefficient, CV. This is the volumetric flow rate divided by U and the square root, okay? So what is the volumetric flow rate in the nominal flow? Cursor, thank you. So I'm going to isolate CV in the expression, and you have here the volumetric flow rate. What is the volumetric flow rate with the valve full open? 24 liters per minute, no? So I convert it to, remember, this 60,000 comes from the conversion, okay, to cube meters per second, okay? So the volumetric flow rate in cube meters per second. Now this U, I go to the curve of the manufacturer and I see that is 10 volts when the Q is 100%, valve fully open, okay? I have an U of 10 volts, okay? So that is why you can find here 10 volts here, okay? And what is the pressure difference when this happens? 35 bar. So you can substitute in the delta P 35 times 10 power to 5 because it's pascals, okay? And this would be the coefficient. Units of the coefficient. What are the units of Q? And we review. Cube meters per second. So you would have cube meters per second in the numerator. U, units of U in this case by the manufacturer, volts, no? So volts and a square root of pascals, okay? So you would compute this value. In the simulation project work, you will have to do something similar with the values that are stated there, okay? But that's the way to compute the CV, okay? So you have already learned, just in case you have an exercise related to this, how to solve or how to compute this constant, this coefficient for a throttle valve and a directional control valve. Clear? Yes? Perfect. Some question related to this computation for the CV? Yes? Clear? Okay. Let's see for the students online, but I think it's clear. And we have 10 minutes left to continue. Good. The computation of this coefficient. Is it clear? Yes. So basically, you have to take into account the volumetric flow rate, the value of the U, and the pressure difference. Okay. Yes. Okay. So let's continue. Well, and this is just an example, okay? In the case of the simulation project work, this tau is provided, okay? The time constant of the valve is provided. Remember that the time constant tau appears in the differential equation, okay, of the spool. This is provided. If you were working in a company and you had to compute it, remember you use the body diagram. You use the body diagram and this expression where this is the frequency associated with the minus 45 degrees in the phase diagram, okay? And you would compute it. Perfect. So now we are going to move to the next component, which is another type of valve. We have already studied throttle valve, directional control valve, and now we are going to study a valve that is called pressure relief valve, okay? You can read it carefully. I have provided some slides. I just want you to understand here the main idea, okay? The main idea of this pressure relief valve. So basically the idea here is that you have a valve from this connection to this other and a volumetric flow rate that is called or denoted by Q1, okay? So basically you have a Q1 that moves from this port to this one, and what happens with this pressure relief or pressure control valve is that you have here a pressure reference, a P2, that helps you to move this valve, and adjust this X position, okay? This X position basically represents the spool, okay? And basically what we want to control is this flow rate Q1 based on this P1. How do we control this? We control this because you can see that you have here a line that communicates with this chamber so that you can send here a volumetric flow rate Q2 and this P2, and with the balance of this elastic force of this spring with the pressure force coming from this chamber, you can adjust the motion of this piston, okay? You can adjust the motion of this piston. The idea that I want you to understand that yes, basically is that the spool equation of motion is complex and controlling the motion of this valve is difficult working with this differential equation, but there is a method called the semi-empirical modeling method that we have already used with the directional control valve or the throttle valve that simplifies this modeling, okay? So instead of working with this equilibrium equation in the spool, you can simplify the control of this valve using these two equations, okay? So basically the Q1 that is shown here, depending on the X of the spool, and the X would come from solving this differential equation, can be computed more easily by just a constant that is K and the square root of P1. And P1 using this semi-empirical method can be computed using this equation, okay? Still, it is complicated because you need to compute different constants, these parameters C1 and C2, but at least this semi-empirical method alleviates the difficulty in the computation of this volumetric flow rate, okay? This is just the idea that I want you to understand. And how does this work, okay? So basically in the spool, you have elastic force coming from the spring, this pressure force in this chamber, and with the balance of this force and the inertia, of course, the piston has a mass, okay, has a mass and a stiffness by itself. You can control the position, and based on this position X and the pressure P1, you can control the volumetric flow rate, okay? That is coming here. This is the main idea. So perfect. And I don't know how much time I have. I have 5 minutes, so I'm just going to introduce the next component, okay? If you think about it, the hydraulic circuit that we built in the tutorial the other day consisted of the pump, that I have not talked anything today, I will talk the next day, the reservoir, then we have the hoses, the directional control valve, more hoses, and the hydraulic cylinder, okay? So now we are going to talk about the hydraulic cylinder, okay? The idea of the hydraulic cylinder is to transform the hydraulic pressure, okay, into a mechanical force, okay, communicated or provided by the piston, okay? And if you think about it, if you isolate this body, okay, basically the force provided by the piston, okay, would be given by, you agree with me that in this side of the piston, there is a chamber of pressure P1, A1, and the force is given by what? How can I compute the force in this side? How can I compute the force in this side? A force is just the area times the pressure, okay? In terms of unit, if you want to understand it. Thank you, Amar. Exactly. Pressure times area. Remember, pressure is Pascal. A Pascal is Newton divided by a square meter, no? So, Pascals, pressure times area, square meters, provides newtons, okay? Which is force. So that is why I have on this side A1 times P1, a force coming from this side. But now you can see that there is also fluid counteracting this pressure force here, okay? So I would have the pressure force in this other side that is H2 times P2. A1 is a what? What is the geometry of A1? It's a circle, right? It's a piston, okay? And H2, what is the geometry of H2? Just in case that you have to compute this in some exercise. Sorry? It's a circular crown, right? So basically you have an external and an internal diameter here, and it's a circular crown, exactly like a ring. Perfect. So you would have here A1, A2, and this F mu represents the friction force, okay? This friction force comes because of the contact of the friction between the fluid with the walls, not only the fluid, but also the piston walls with the chamber walls, okay? So basically what you can read here, seal material and the cylinder wall cause this friction force, okay? And of course, do you remember the response that we obtained in the tutorial? If you remember, we obtained an evolution of the pressure that had a lot of oscillations, okay? So if friction increases, this is a way to reduce these oscillations in the hydraulic cylinder, okay? So this is the force provided by the piston, mechanical force, okay? Now, this slide is more focused on the friction force, okay? So in hydraulics, the modeling of friction force is really complicated. There are a lot of models. A very famous model is Brown and Maffei model, just in case any of you want to read about this. But in general, it's a phenomena that is really complicated and depends on several factors, as the speed of the piston, the pressure difference, the direction, the material type. So many factors appearing, okay? But typically, a possibility to model this friction force can be seen here. So basically, what you would have is the force basically given by the difference in the pressure force times this function of the speed of the piston and times this factor where eta is the efficiency coefficient, okay? This Greek letter, eta, is the efficiency coefficient, okay? And this function is dependent on the speed, and it can be obtained by measurements or different models, okay? Different models. So basically, this is the idea. Remember, this F mu, the friction force, appears in this side, okay? And the model, one possibility to model it is given by this equation, okay? Where eta is the cylinder efficiency, okay? Let me check the time. Okay, it's 2 minutes left. Okay, so I think it's a very good point to stop here, okay? We have learned, I think, a lot today with different components. So do you have any question about the throttle valve, directional control valve of the cylinder? Everything is okay? Yes? Perfect. So for the students online, everything is good, okay? If everything is okay, I will stop the recording. Please, before you go, tomorrow we have the tutorial 7. I highly recommend you to attend to the tomorrow's tutorial because we are going to work with the same example as the previous day, but I'm going to tell you how to program the hydraulic cylinder and the directional control valve, because in the simulation project work, you need to do it this way. So basically, we will work with the same example and we will customize this directional control valve and the hydraulic cylinder. Everything we have studied today, okay? And that's it. And remember, for the tutorial of tomorrow, install the Simulink Control Design Toolbox, okay, for the static equilibrium. Do you remember that we discussed about it the previous day? So install it. And tomorrow, once we complete the tutorial, you are completely capable for completing the simulation project work, okay? So see you tomorrow, as usual, okay? Thank you for the students online. Do you have any question? Everything good? Okay, thank you. So I will stop the recording now. Thank you.